Introduction. I'm not feeling very well today, so I'm sorry if you can't hear me very well. I'm Thai from Google Security, and I'm here to present to you Project Breach-Proof. So at Google, I have 50 minutes, so I will talk very quickly so that we have some minutes for the question and answer. At Google, we use crypto in many products. And I think this image captures how we do product crypto at Google very well. So most of the time, a product team want to implement some security or privacy features, and they come to us and ask us to develop that feature for them. So what we do is we look at the feature, we develop a protocols. For example, if they want to do end-to-end encryption, or they want to do storage encryption, or they want to cite some URLs. Then we design and implement this protocol for them. And the protocol are usually built on top of internal robust APIs that we develop in-house. These APIs basically implement the common crypto operation, like authentication encryption, signature, or hybrid encryption. And these APIs, in turn, are built based on third-party open-source crypto libraries like OpenSSL, OpenJDK, Pacicacho. I name these libraries just because we use them. It's not because they are better or worse than other libraries. The problem is we usually find that this library usually have a lot of bugs, and these bugs happen for a long time, and they repeat themselves very frequently. Like there are bugs that that should be fixed 10 or 14 years ago, 15 years ago, but somehow they are not. And when we look at the libraries, we were very surprised. And another problem is we find out that it's very hard to write good crypto implementation guidelines for even smart software engineers. They don't have the necessary background to basically implement crypto correctly. And getting crypto correctly requires digesting decades worth of academic papers. And of course, we security engineer can review the libraries manually ourselves, but that is not scalable because there are lots of libraries out there. Another major problem we have is we find out that sometimes we find a bug, we fix them in our internal copy, and then we report it upstream, get them fixed in upstream, and then only to see them coming back when we upgrade our internal version to a new version of the external library. And regression like that really hurt because we can't just go back and review every single changes to the libraries. So there should be a better approach. And with those observations, we recognize that basically software engineers, they prevent and fix bugs by using unit testing. And we think that crypto issues, many crypto issues can basically resolve by the same means. So these observations have prompted us to develop Project Breach-Proof, which is basically a set of open source unit tests that the tests check the crypto libraries for known problems or some expected behavior. And so far, we have more than 80 unit tests. And when we run the test against the libraries that we use, we found more than 40 bugs. We have tests for elliptical crypto as a Diffie-Hellman authentication encryption or big integer array method. Most of the tests are defense in depth. Basically, we want to make sure that the libraries expect in the right way. Sometimes we don't check, rather than just checking for exploitability. We just want to make sure that, for example, default values are reasonable. For example, today, when you run the test, the test would we consider it's not okay for a library to generate as a key with with a default value of 1024 bits, or using DSA, a digital signature with using SHA-1 as default. And there are many more tests in where we check that the library actually are not vulnerable to, for example, timing side channel. We also release out-of-the-box test runners for the libraries that we use, like Basic Cache, Spongy Cache, and OpenJDK. Our goal is to make it very easy for the user to run a command line and to be able to test the latest version or some particular version of the libraries that we support. So, any questions so far? So, in the next two slides, I will show you some of the cool bugs that we found. The first one is the key recovery in OpenJDK's DSA's implementation. So I think these bugs were fixed in April last year. The problem here is the DSA implementation actually allows, if you look at the red line, the sign object is used with a private key with like 2048 bit. The problem is if you initialize the signature object like this, OpenJDK will always generate the nonce using 160 bit only. That means the nonces are heavily biased. And that means you can easily recover using like latex techniques the private key just by observing 3 to 5 signatures. And this is a critical problem because DSA is still used a lot in many other places. Any question about this bug? The second bug is also a key recovery in Basic Cache, elliptical Diffie-Hellman. The C in the last C stands for cofactor. Basically, when they compute a shared secret, they multiply with the cofactor. And if you look at the red line, the way they compute the shared secret is they take the private key, which is key.getD, which is the private key of the receiver, and they reduce it modulo the order of the public key, which is under the attacker control. That means, we can change, like the attacker, the X509 standard allows the attacker to change the order of the public key. So we can change the order of the public key and to binary search for the private key, because we can tell whether the private key is larger than the order, and then we can change the order to see, like, to finally nail down the range of the private key. And it just took like, I don't know, like a few requests, like maybe 100 requests to recover the private key. So these are the two, like, I think, coolest bugs that we found. But there are also many other bugs. Like you can look at our project on GitHub, and I think in last week, Basic Cache just released the latest version, and they fixed like 8 or 9 bugs that we found and reported to them. So working on way to proof allows us to basically to understand what text like how a good crypto library should look like. And one of the things that we've observed is there are not a lot of good crypto libraries out there. For example, we have crypto libraries that ask user for retoken input. Like if you want to encrypt something, you have to pass in a random number generator. And it's impossible to test those libraries because even though if we test the library, the user can easily screw up by passing in an insecure random number generator. We also find out that most of the libraries out there don't actually allow users to switch the algorithms easily. So if you switch the algorithm, you have to start from scratch. And the ciphertext encrypted with the old algorithms won't be compatible with won't be able to be encrypted by the new software. Another property that we want to see in crypto libraries is it should be easy to look at the code and understand right away the crypto properties guaranteed by the libraries. Like for example, if you are using authenticated encryption, then it should be very easy to look at the code and understand right away without having to navigating the whole structure of the libraries to go down the abstraction layer to understand what's the properties guaranteed by the library. Another problem that we saw is we would like to see the crypto community to develop a common crypto interfaces for C++, Python, Go, or JavaScript. We have something for Java, which is the Java cryptography architecture, but we don't have anything for these languages, and it's very hard for us to write tests without having a common crypto interfaces. We actually, right now what we do is we try to translate most of our unit tests into text vectors, into raw text vectors, so that people can easily port them to other languages or platforms. But it would be nice to have one single set of, just to write the test once, and we can run it everywhere. Here's other few useful links that you can look up. On the source code documentation have been released on GitHub. We also have a mailing list where we take request support. Like if you want to test something, or if you want to run the test against some particular libraries that we don't support, please email us and we will take a look and see if we can support you. The mailing list also is the place where we discuss what the new updates, the major tests that we are going to release in the next few months. So we are actively working on adding more tests, and not only for primitives, we also want to test protocols like SSL or JSON web encryption. We look at those libraries and we found lots of problems. So and those libraries are getting very, very popular these days. So we want to make sure that we can test them and making sure that we can, help the developers to fix the issue. Most of the tests that we release, we have been working with, Bicycastle, OpenJDK, to integrate these tests into their, CI system so that they can avoid, regression. I think that's it for my presentation. Oh, this is the people working on the library, or the project. All of us are from Google security team, but we welcome external contribution. I think so far we have got at least a few PR requests from external people. So please keep it coming. Keep them send us anything that you want to improve in the project. Yeah, that's it. Thank you. If you have any, I think we still have 5 minutes for questions and answer. If you have any comments or anything that you want to test, and I want to have a commercial break. My team is hiring, and if you're really interested in building and breaking, crypto used in products that used by billions of people, please come and talk to me, or send your resume to my email address. Thank you.
Okay, so we do have some time for questions, and I see somebody at the mic, so take it away.
Hello, interesting talk. I'm Yao Qi from National University of Singapore. So one quick question. So suppose the open source library like OpenSSL fix a bug with some patches. How long does Google take to update the software on the user's client side?
You mean like how long we update the
Yes.
internal copy?
No, not internal copy, like deliver the software to all the client-side users.
I'm not sure I'm the right person to answer this question. I think probably Adam and Emilia are the right person to answer this question. But basically, I think we try to push the updates to the client user, like to our user before we release, the information on the vulnerabilities or the bugs. So if you see a vulnerability release or adversary, usually the bugs have been fixed in the user machines already.
I see. So there is a very short window for the attacker to attack your software.
I'm not sure it's the case because sometimes the time it takes for, it takes us very I think it should take us very short amount of time to fix the vulnerability. But the time it takes from the people who find the vulnerability to report it to us, maybe during that window, somebody else have, got their hands on the knowledge of the vulnerability. But it should be very, very quickly. And the windows, and we do our best to make sure that the window is very small, like maybe a few days.
I see. Thank you.
Yep.
Hello. Thanks very much for doing this work because it looks really interesting.
Thank you.
And I had a question about, you had a bullet point there about switching algorithms by applications, and I'm wondering if you can kind of expand on that a little bit and talk about what exactly the problem is that you're trying to solve with that and what that exactly means.
Yeah, it's just an observation. When we look at the crypto libraries, open source crypto libraries, we found out that most libraries don't allow users to switch the algorithms easily. Like for example, if you use encryption, if you have a bunch of data, you encrypt the data and you send, for example, you encrypt some URL parameters, and you send those parameters around the world, and they are embedded in links that are publicly. You can't change the ciphertext anymore. And now you find out that, the algorithm that you are using may not be very strong, and you want to switch to something else. The problem is when you want to do that, most of the time you can't decrypt the own ciphertext anymore. And that's a big problem, right? Because you want to be able to still decrypt your own ciphertext, your current ciphertext, without having to completely rewrite your application.
Right.
So most of the time, I think it boils down to basically you have to making sure that the ciphertext contains some metadata about the key that you use to encrypt, to generate the ciphertext. And there's some techniques that you can use to very simple idea, you can embed a key ID or something into the ciphertext. But some standards actually, instead of embedding a key ID, they do things like they embed the key ID as well as some algorithms parameters about that are used to generate the ciphertext, like the key ID, algorithm, and for example, if you look at JSON web encryption standards, they have key ID, the algorithm that was used, and then some other parameters. And I think that is wrong because you shouldn't do that because you just specify the key ID, and the key ID should be bound to all of those properties. So when you look at the key ID, you have all the information in your configuration to decrypt or verify the ciphertext.
Right, so basically what you're saying there is that, because most crypto designers, protocols, and APIs are looking to prevent downgrade attacks, for example, so they actually limit options deliberately. So it sounds to me like you're talking about techniques that both avoid these kind of attacks,
right,
but also provide this ability to switch algorithms.
Yep.
Okay, thank you.
Mm-hmm.
Okay, is it a quick question?
Yes.
Okay.
So on slide 2, I noticed something very interesting. The APIs you're providing to developers implement very basic things like encrypting, authenticating encryption, and yet you use libraries written for these purposes, and apparently the APIs aren't suitable at all.
Sorry?
Apparently, the APIs those libraries provide can't be exposed for this purpose. So what's the benefit from using those libraries? Why should there be a plurality of libraries that all don't work instead of one that does work and provides the right algorithm so you don't make this mistake of using the wrong algorithm with an API that's easy to use?
So if you look at crypto libraries, there are, I think, several levels, like low-level libraries like OpenSSL, OpenJDK, Bicycastle. They provide us the primitives, like, AES, elliptic curve, Diffie-Hellman, all of those primitives. But if we let the programmers to use those libraries directly, usually they use wrong. So what we want to do is we want to give them a kind of a mid-level library that abstract away the common crypto operation that we see that are deployed in many use cases. So, and those applications, those common crypto operations are usually just 4 operations, like authentication encryption, MAC, hybrid encryption, and digital signature. There are other things like deterministic encryption, but they are less popular than those 4 primitives. So what we do is we develop those, primitives, those interface, and provide our programmers, our developers, those interface. Of course, we don't let them to use those interface directly either. In order to use them, they have to talk to us, because most of the time we want to make sure that they use the right primitive for the right application. So does that answer your question? Thank you.
We're already running slightly behind time, Rich, so I suggest any further questions, we take them to the break, but let's thank Ty one more time. Thank you, Ty.
Thank you.